We are back to our acid-base notebook with Chapter 19, a strong acid, strong base titration. 3 times 10 milliliters, that's there for sig figs, I think, 3 sig figs, of 0.500 molarity hydrochloric acid was titrated with 0.500 molarity sodium hydroxide. Determine, and then we have 4 different states here, the initial pH before the titration begins, the pH after 15 milliliters of the titrant is added, the pH when 30 milliliters of the titrant is added, and the pH after 45 milliliters of the titrant is added. Okay, so let's just get started. Oh, I don't want A. 1. So we always start by identifying our major species. So what are the 2 things that we're working with? We're working with hydrochloric acid, which we know is a strong acid, and if you don't know it's an acid, well, I'm not sure what to say. The next one is sodium hydroxide, which we know is a strong base. All right, next we're going to, as usual, write out our reaction. Okay, well, we know that when you add a strong acid to a strong base, you end up with their salt and water. If you wrote these equations out separately, that's fine. Just make sure that you are able to get the net ionic, because that's what we really want. The net ionic is what we use for our ice charts. You would end up with H plus OH minus reacts to form H2O. Now, this is always true for strong acids and bases. However, you do want to be careful of when you have something that is insoluble, an insoluble salt, because that might shift your net ionic a little bit. However, basically always true for strong acids and bases right here. Okay, now let's get into the meat of the problem. Part A is asking us to figure out the initial pH. So let's do that. Solve for initial pH. Now some of you are probably wondering, why didn't she write an equilibrium expression? Why aren't we doing an ice chart yet? And well, these are strong substances. Do we need an equilibrium expression? No, we do not. We do not need an equilibrium expression if they are strong substances. So I can just go ahead and solve for my initial pH. This is, let's see, what is our initial substance? Hydrochloric acid is being titrated with NaOH, so I want the pH of my hydrochloric acid. I know that I have 0.500 molarity HCl, and it's going to end up reacting to form 0.500 molarity hydrogen and 0.500 molarity chloride. It's a 1-to-1 between everything, so it's easy to figure out. Okay, well, I need hydrogen in order to figure out the pH. pH is, what's pH equal to? In this case, we want to use that it's equal to the negative log of the hydrogen ion concentration. So you should end up with a pH equal to 0.301. Remember, when something goes through a log, the sig figs only matter after the decimal. Well, in this case, it doesn't look different than what we do usually. So this is part A. There's our initial pH. It's a very, very low pH. Does that make sense? Well, hydrochloric acid is strong, so yeah, makes sense. All right, now we are going to move on to part B, which is the pH after 15 milliliters of the titrant is added. oops, that should be a period there, 15 milliliters of our titrant, so the thing that we are adding with the burette, NaOH. Okay, so then first, well, we are mixing together two different volumes, which means we need to do a dilution. Let me just scroll down a little. So we'll split this into two. HCl. We know our hydrochloric acid starts off at 0.500 molarity, and we have 30 milliliters of it. And that's equal to the new concentration that we want. And we have added 15 milliliters to the original 30, so its new volume is right there. Okay, so you should end up with an initial concentration of your hydrochloric acid of 0.333 sig figs, and we know that means that we have that molarity of H plus and Cl minus, because the hydrochloric acid dissociates completely, so that's how much hydrogen we get. So our sodium hydroxide, let's do the same thing. That one also started off at 0.500 molarity, but that one we had an initial volume of only 15 milliliters. We want to know our M2, and it had the same final volume. So for NaOH, the M2 is equal to 0.167, which tells us the concentration of its ions, because sodium hydroxide completely dissociates as well. So we know we have that concentration of Na plus and OH minus. All right, so now, after we've done our dilution, we are going to figure out how much hydrogen and hydroxide we have after they're done reacting with each other. So you don't have to do an ice chart, but you can. So I'm going to, just so you can see the opportunity you have here. You have I, C, E. Now remember, we are going to use our net ionic here. We use the net ionic, which we found up at the very beginning. H plus OH minus H2O. You could put the whole thing in there, not net ionic, but if you did that, you'd end up with really boring numbers, more work than you need. Okay, so I know from my dilution how much hydrogen I have. I know how much hydroxide I have. And I know that I don't include water because it's a liquid. Okay, so in this case, do I know my ending concentrations? Well, I mean, I know that in these strong substances, all of the hydrogens and hydroxides are released, and I know that hydroxide is my limiting reactant, so it's actually going to get used up completely, which means that since we have a one-to-one between it and hydrogen, so this is the benefit of, here, if you do that subtraction, look at this. This is the benefit of doing ice charts for strong substances. You don't have to use X's. So you could put that here. Don't need X for strong substance ice charts, because they are very predictable. We know everything that's going on with strong substances. Okay, so now we've done that. So now that we know all our concentrations, we can solve for pH, which was the goal of part B. All right, so let's see, pH is equal to the negative log of the concentration of hydrogen ions. So you should end up with a pH of 0.78. I want 3 sig figs 0. This is for part B. So let's see if this makes sense. In part A, our pH was 0.301. We added some sodium hydroxide and the pH was raised to 0.780. Does it make sense that the pH went up when we added a base? It should, hopefully, because bases, their pHs are higher. So that's what ended up happening there. Okay, now we're moving on to step 5. We're going to solve for the pH after 30 milliliters of NaOH have been added. So first, okay, we've added a different volume, so we need to do the dilution again. So these steps are a little bit different than what we've been doing in the notebook so far. However, they are very repetitive. You do a dilution, you do an ice chart, you solve for pH. Dilute, ice chart, pH. Dilute, ice chart, pH. Over and over and over again until you're done. So HCl, we know we go back to its initial concentration and its initial volume. Oops. And then we have new. So you could do this without me, probably. You could mute the video and just kind of go for it and see what happens. So I found out the concentration of my hydrogen and my chloride ions. Now I'll do the same for my sodium hydroxide. Also 0.500 molarity. And this one was also at 30. And oh, would you look at that? All the numbers are the same. Interesting. Oops. So if you watched the notes video before this, which you should have, the titration notes video, you might notice like, hey, the number of moles of my titrant are equal to the number of moles of what's being titrated. We call that the equivalence point. Because the moles of what's being titrated are equal to the moles of our titrant. This will be important later because we're going to try drawing a titration curve. Okay, so now that we've got that, my end goal is to solve for pH. I need to know how many hydrogens I have at the end, so let's make an ice chart. Again, this is doable without an ice chart if you want to just do the subtraction in your head. But for the sake of being as thorough as possible, I will write it all out. So we know we have 0.250, 0.250, and this doesn't count because it's a liquid. And oh, they're equal. There is no limiting reactant. So they're both completely used up. Interesting. Well, then let's use that to figure out the pH. So if they are both at 0, well, then where are our hydrogens coming from? If not from our acid and base, they come from our water. So we'll have this. at 25 degrees C, we know that. So you can figure out, okay, well then we have a concentration of hydrogen ions equal to 1.0 times 10 to the negative 7, which will give us a pH equal to 7. How many sig figs do we have here? It depends on how many sig figs you say this has. Let's go, I think usually we'd give 2 zeros after that. So there's our pH. Okay, so again, what you'd want to make sure you know is that at the equivalence point, the moles of hydrochloric acid are equal to the moles of sodium hydroxide. And another important note that you could make is that at the equivalence point, oops, oh my gosh, looks like a V. At the equivalence point, the for a strong acid and base, strong acid plus strong base, the pH is equal to 7. So that's a helpful little note too. Okay, so now let's move on to 8. And this back here was, what was this? This is question C. So now we're going to solve for pH after 45 milliliters of sodium hydroxide is added. Oops. Okay, if you have not tried this on your own without me yet, you should now. Definitely, you don't need me. I'm not going to write out the steps, I'm just going to do this. I'm doing my dilution. So this time it's at 75 milliliters. So our M2 is 0.200 molarity H plus and Cl minus. For this, we started off with 45 milliliters, same final volume, and you end up with 0.300. So now that I have my dilutions done, I can create my ice chart, which again is not strictly necessary, but I'm trying to be thorough. That goes away. 0.200, 0.300. So what's our limiting reactant here? That would be our hydrogen, so that's what I'm going to subtract from both sides. I end up with no hydrogens, but I do end up with hydroxides. So when I go to solve for my pH, I'm going to have to find pOH first. That'll give me a pOH of 1.000. So that means my pH must be equal to 14 minus 1.000, which gives me 13.000. This was the answer to part D. Now, this question did not ask us to draw a titration curve, however, you should know how to do that, so I'm going to just add it on there. Okay, so we're just a sketch. So you're going to want to know your pHs and your different volumes in order to do it. Okay, I'm going to draw my general little swoopy lines. Okay, I know that, here I'll use blue for this, at 30 milliliters, I was at my equivalence point. You will know why I'm putting these lines exactly where they are if you watched the Titrations Notes video. So here we have the volume of NaOH versus pH. Here is our equivalence point. And I probably didn't draw this perfectly, but if you wanted to make this scale even better, let's see, we know our initial pH was less than 1, so we'll do that. And if I was on graph paper, I'd say, okay, well, at 15 milliliters, the pH was this, and at 45 milliliters, the pH was that. However, our starting pH and our equivalence point are what is most important. So here is our basic titration curve.